What I'd like to talk about in this video is the categorical notion of an end. So an end, often written in this sort of integral fashion, the integral sign C in some category T of CC, and T here is supposed to be a functor from the opposite of a category crossed with that category to a different category. And so an end is supposed to be some object in this category which is a bit sort of limit-like in a certain sense, which I will describe. So ends are not quite as common as the dual notion of coends, I don't think, and I don't think they're as intuitive either. I think they're a bit more mysterious perhaps to people not so familiar with them, and I think the integral notation is certainly more appropriate for the coend situation. But places where ends do crop up include the idea of natural transformations. So we'll look at this next time. So natural transformations, especially when you're thinking about enriched category theory and you're looking at objects of enriched natural transformations. And the other place where I know these crop up is certainly in reconstruction theorems. So reconstruction theorems is when you start off with a category and you want to, or you believe that is the category of representations of some algebra type object, some monoid maybe. So you have, well, you can either start with an algebra type object, build a category of its modules, and then try and reconstruct that algebra in some way. There's various ways you can do that, or you could just start off with a category that looks like it's a category of representations. Maybe it's a closed monoidal category and you want to find what the object was that it sort of the modules over. Okay, so this is known as sort of Tanaka reconstruction. So there are sort of two places where you might come across ends. I'm sure there are more, but these are the ones that I'm sort of familiar with. Okay, so I guess the best thing to do is to give a definition. And then next time I will give sort of plenty of examples of these things. Well, a handful of examples at least. Okay. So, like a limit, a coend has a certain universal property, so it's universal with respect to wedges. So I'll describe first what a wedge is. So a wedge, which I'll write as x to t with a dot on the arrow, so consists of an object x in the target category D and a family of components. So these are, what are the components? So like components of a natural transformation. So whoops, there should be a C. So for each C in C, we have a morphism in D. So this is a morphism in D there. Okay, and these have to satisfy a certain naturality type condition, so they have to be compatible with each other in a certain way, such that the following diagram commutes. For all f from C to C prime. So for each C to C prime, we're going to get a diagram of the following shape. So we can go from x, we've got the component sending it to TCC, or the bit sending it to TC prime, C prime. Now we've got this extra bit of data here, a morphism from C to C primed, so this is a morphism, in case it wasn't obvious, in C. Now T, importantly, is covariant in the second variable and contravariant in the first variable. So we can apply t to f in the second variable here, or t to the first variable here, and in both cases it'll send us to t c primed. Okay, so here we just go from c to c primed. Here it's contravariant, so we're going from c prime to c, but keeping the second variable fixed. Okay. So we need that to commute for every morphism in C. So this condition is sometimes called dinaturality. Or possibly extranaturality. So the di here, I think, stands for diagonal, meaning that you were just looking at the diagonal terms here where we get CC. Okay. So that's what a wedge is. So a wedge is an object with all these properties. So it's like, in some sense, it's like a cone, really. It's a generalization of a cone. I'll explain how it's a generalization later. Okay, so now, an end is a universal wedge. So i.e., so it consists of some wedge from E to T. Let me just separate that off. So it consists of a wedge from some object E into T, such that if X is a wedge for T, then there exists a unique morphism in D from X to E, such that the components of X factorise through the components of E using this map, such that components factorise factor through this. So in other words, we get X to T CC factorises through this map and the components for E. Okay. So hopefully you see that's a sort of limit type definition, and I guess the important thing to do at this point is look at some examples, so that's exactly what we'll do next time.